Hello and welcome to another lecture of classical motion of a single particle. In this lecture, I will discuss a little bit more about damped harmonic oscillator, and also I will discuss an interesting problem on damped harmonic oscillation. So, we just remember what we have done. So, we have said that if one particle is just undergoing simple harmonic oscillation in the absence of any forcing or damping, then the equation of dynamics in 1D is given by this, where omega 0 is the natural frequency of the particle. So, omega 0 is the natural frequency, and we have also assumed that in general the equation is given by the solution of undisturbed freely oscillating oscillator is given by some A cos omega t omega 0 t plus B sin omega 0 t, and then we have said that we can also write in a compact form like this: A cos omega 0 t plus some alpha, okay, where alpha is the initial phase or the epoch and A is the resulting amplitude. Okay. You can always write that by choosing smartly A and B in terms of small a and alpha. Okay. Now, the question is, let us say I have an oscillator. Okay. The oscillator is first, the system of oscillator is not changed. Okay. So, the oscillator is first let to oscillate without any damping or any forcing. Okay. And then the same oscillator, so the same oscillator is again put in a viscous medium of damping coefficient lambda, and we consider lambda is actually greater than omega 0, and that is why we have what we called an overdamped motion. In this problem, we will try to find the ratio between the maximum velocity in the first case and that of the second case. Okay. So, let us say if I say V max 1, here the maximum possible speed velocity in so just in 1D, so it is just the speed. So, maximum possible speed, okay, in the first case where the particle is freely oscillating, and if we have the same V max in the second case as V max 2. So, that will be the maximum speed in the second case. We will find the ratio chi, which will be simply V max 2 by V max 1, okay, and we will find that in different limits. Okay. So, in general the problem looks very easy and the problem is actually pretty straightforward, but we have some mathematical techniques over here, and that is exactly we will do in this exercise. So, first I am talking with the case 1. So, case 1, okay, I have x is equal to A cos omega 0 t plus alpha. So, x dot will be A omega 0 sin omega 0 t plus alpha with a minus sign. This is d dt of x, simply this one. Okay. And if I write, then I will say, okay, in order to now understand the exact solution, or the like the specific solution for this problem, we want to have some initial condition, and that is why in this problem we say that the initial displacement is equal to x0 and the oscillator always starts from rest. So, initial velocity or initial speed is equal to V0 is equal to 0, that we will use. If we use here in this case, so at t is equal to 0, you will have x0 is equal to a cos alpha, and if I call this as V, so V0 will be equal to minus a omega 0 alpha sin alpha. Okay. And this quantity is actually, so this one is actually 0. Okay. So, we say that alpha is equal to 0 or any multiple of 2 pi, that we just neglect for instance, we just simply say that alpha is 0. Okay. And so, x will be equal to x0 cos omega 0 t. Okay. And V will be equal to simply x0 omega 0 with a minus sign sin omega 0 t, and what will be then the V max, that I write in another color. V max 1 will simply be equal to, so this is actually for the first case, that is why I put this index 1 over here. V max 1 will be equal to mod of minus x0 omega 0. So, this will be maximum when sin omega 0 t will be 1, and that will be x0 omega 0. Okay. This is pretty easy. Now, how to find the maximum velocity in the second case? So, now case 2, we consider case number 2. This is the case of overdamped oscillation. Overdamped oscillator is moving over here, and x of t will be simply given by some constant which is real here in this case, C1 e to the power minus lambda plus root over lambda square minus omega 0 square times t plus C2 e to the power minus lambda minus root over lambda square minus omega 0 square times t. Okay. I call this thing as omega d, so that you can have something like omega d square will be equal to lambda square minus omega 0 square, that we can use from time to time, this thing. Okay. Okay. Now, everything is real over here, C1, C2, lambda, omega 0, all are real. Okay. And also we know that lambda and omega 0, they are positive as well. So, here lambda is positive, omega 0 is also positive by construction, that is how we choose. Okay. So, here we know, then I can write this is equal to C1 e to the power minus lambda minus omega d t plus C2 e to the power minus lambda plus omega d t. Okay. This is my displacement. Now, what will be x dot or the speed, okay, here? So, that will be simply d dt of this quantity, and which will be minus C1 lambda minus omega d e to the minus lambda minus omega d times t plus there will be another minus which will come actually here. So, I again take this minus over here, and C2 lambda plus omega d e to the minus lambda plus omega d t. Okay. So, this is the d dt of the displacement, and now I am saying that at t is equal to 0, x is equal to x 0 and v is equal to 0. Then what happens? So, first thing here I will take that, then I will have x 0 will be equal to, so C1 this term will be 1 at t is equal to 0, this as well. So, it will be simply x 0 will be equal to C 1 plus C 2, okay. And V 0 which is equal to 0 actually. So, 0 will be equal to this thing, because this thing at t is equal to 0, and that will be again minus C 1 lambda minus omega d minus C 2 lambda plus omega d, okay. So, if you have now this, then you can write C 1 lambda minus omega d is equal to minus C 2 lambda plus omega d, okay. And you can write always that C 2 is equal to x 0 minus C 1. So, C 1 lambda minus omega d is equal to minus. So, minus C 2 actually you can also write as, so this minus C 2 you can just write C 1 minus x 0. So, it will be C 1 minus x 0 times lambda plus omega d, and you will have C 1 lambda minus omega d minus lambda minus omega d is equal to minus x 0 lambda plus omega d. And finally, you will have, if you do it correctly, you will have C 1 will be equal to simply x 0 lambda plus omega d, and here from this side you will have a 2 omega d will come, and you will have a global cancellation of the minus sign. So, it will be 2 omega d, okay, and you have a solution for C 1, and similarly you can also find C 2 will be equal to minus x 0 lambda minus omega d by 2 omega d, okay. So, finally, you are all set to write the general solution with, I mean, already knowing the arbitrary constants of integrations in terms of the initial conditions. So, then your x will be simply x 0 by 2 omega d lambda plus omega d whole to the e to the minus lambda minus omega d t. Here you see that already I have put the values of this constant C 1, okay. So, if you just follow this thing, okay. Yeah, sorry, if you just follow this one, yeah, this one, and then you will have minus lambda minus omega d e to the minus lambda plus omega d times t, okay. And similarly, you have for velocity or the speed here the same thing in 1D, okay. So, x 0 by 2 omega d. So, of course, velocity is a vector, speed is a scalar, we all know. I mean, just trying to say that here we do not have to consider different components of velocity, that is what I am meaning, okay. I am not saying that velocity and speed they are exactly the same quantities, okay. So, yeah, if you now write again, so you will have lambda square minus omega d square, okay. Here also you are just putting the value of C 1 and C 2 in this expression now, and you will have. So, basically the best thing is to check by yourself, okay, e to the minus lambda minus omega d times t minus lambda square minus omega d whole square e to the minus lambda plus omega d t, okay. If you are done with this expression, then you can easily understand that this expression is a very interesting one, because this lambda square minus omega d square is nothing but omega 0 square from this one, okay. So, lambda square minus omega d square is omega 0 square. I take the omega 0 square out and I can write minus x 0 omega 0 square by 2 omega d e to the minus lambda minus omega d times t minus e to the minus lambda plus omega d t. Okay. Now, I will try to this is the velocity expression of velocity, where you know all the initial conditions and then you express the arbitrary constants of integration in terms of them, then you do the ddt. So, that is something also a training to understand for general problems. You do this thing that first you express the velocity in terms of the known quantities of the system, and then only you take the derivatives, otherwise you will never get rid of the arbitrary constants of integration. Okay. So, for V to be maximum, now this has to be maximum. So, for V to be maximum, we need dV dt is equal to 0, and I mean of course at V is equal to V max. Okay. I mean I am just saying that this is something we have to have at one specific value of velocity, and for that specific value if you also evaluate d2v dt2, then that will be less than 0, that will be negative, that is the maximum condition. So, I will first do this one. Okay. So, dv dt is 0 means this is constant minus x 0 omega 0 square by 2 omega d, and then you do so minus lambda minus omega d e to the minus lambda minus omega d times t minus e to the so yeah, we have to take again this. Okay. So, there will be a minus again will come. So, it should be plus lambda plus omega d times e to the minus lambda plus omega d t. Okay. And this is equal to 0 for some velocity value, okay, which is V max, that we can say. If this is true, then we can actually say, okay, my e to the minus lambda minus omega dt times lambda minus omega d will be exactly equal to e to the minus lambda plus omega dt, okay, times lambda plus omega d. Okay. That is the condition for this to be 0. And here you see there is one e to the minus lambda t and e to the minus lambda t which can get cancelled. Okay. And then we can actually have, so we can have e to the plus omega dt, here also you have e to the minus omega dt. So, we can take them together. So, that will be e to the 2 omega dt, that will be equal to lambda plus omega d by lambda minus omega d. Okay. And then finally, you can say that, so you just take the logarithm, natural logarithm of both sides. So, you will have t 2 omega dt will be log of this expression. So, t will be 1 by 2 omega d log of this expression. Okay. And now, of course, if you check, so for this t, if you check d2v dt2, you can show that this is also less than 0, and that is something I want to leave for you as an exercise. So, if you now just believe that this is the value of t for which velocity is maximum, then what will be the maximum velocity that we have to find? So, that will be v at t is equal to this 1 over 2 omega d log lambda plus omega d by lambda minus omega d, and then that will be actually minus x 0 omega square by 2 omega d, and then you write e to the minus lambda minus omega d in the place of t you just write 1 over 2 omega d log lambda plus omega d by lambda minus omega d. Okay. And then minus e to the minus lambda plus omega d, again for t you write 1 over 2 omega d log lambda plus omega d by lambda minus omega d. Okay. And then e to the something, so this is like this, e to the a log b is nothing but e to the log b to the a, which is equal to b to the a. So, that we will use here. Okay. So, minus x 0 omega square by 2 omega d. So, you see that this will be simply e to the log lambda plus omega d by lambda minus omega d whole to the minus lambda minus omega d by 2 omega d. Okay. And then minus e to the log lambda plus omega d by lambda minus omega d, whole to the minus lambda plus omega d by 2 omega d. These things you have to understand, that if you can do that, then everything is done, and you can write minus x 0. I can actually write omega 0 everywhere. I do not know whether I missed it over here. Yeah, omega 0 is there. Okay. Yeah, 2 omega d. And then what will be this? This is simply lambda plus omega d by lambda minus omega d times minus lambda minus omega d by 2 omega d. Minus, here there should be a minus, I should erase this, otherwise it will be confusing. Yes, lambda plus omega d by lambda minus omega d minus lambda plus omega d by 2 omega d. Okay. So, this is something I think we can all do. Okay. And then since there is a minus sign, you can actually take something. So, minus x 0 omega 0 square by 2 omega d, you can actually take this thing like, so I can actually say that you can take one thing common over here. So, that is lambda plus omega d by lambda minus omega d, okay, minus lambda to the power 2 omega d. That you can take common from both sides, and from the first term you will still have lambda plus omega d by lambda minus omega d to the power. So, that should be plus omega d by 2 omega d, which will be plus half, then there will be a minus sign, and I will have lambda plus omega d by lambda minus omega d. Here again you will have minus half. Okay. Now, this thing is nothing but lambda minus omega d over lambda plus omega d to the power lambda by 2 omega d. Okay. So, I will exactly write that. So, V max will be equal to x 0 minus x 0 omega 0 square by 2 omega d, then the first factor is this one, where I take this minus off, so that they will, the numerator will go to the denominator will go to the numerator and vice versa. So, lambda minus omega d by lambda minus omega d by lambda plus omega d whole to the lambda by 2 omega d. Inside the bracket, you will see there will be a very interesting simplification. So, this term will be then, yes, so lambda plus omega d by lambda minus omega d whole to the half, there is a minus sign, yes, and then lambda minus omega d by lambda plus omega d, there will be also a plus half sign, because this is lambda plus omega d over lambda minus omega d whole to the minus half. So, I can just invert this. Okay. And then what is this? So, this you can actually calculate, you can say this is nothing but, so lambda square minus omega d square whole to the half, then I will have lambda plus omega d minus lambda minus omega d, that is plus omega d. So, I will have actually 2 omega d. What is again lambda square minus omega d square? Lambda square minus omega d square is omega 0 square. Okay. So, this is omega 0 square whole to the half, that is omega 0. So, I can now write V max will be simply equal to minus x 0 omega 0 square by 2 omega d lambda minus omega d by lambda plus omega d whole to the lambda by 2 omega d times 2 omega d by omega 0. 1 omega 0 I can cancel, omega d go away, 2 go away. Then I finally will have is equal to minus omega 0 x 0, okay, lambda minus omega d by lambda plus omega d whole to the lambda by 2 omega d. So, this is my V max 2, and if you remember my V max 1, my V max 1 was simply this thing, actually this. Okay. So, if I again take the modulus of this, okay, you will have this, and then so the chi which I want to determine for this problem is equal to V max 2 by V max 1, of course, in the modulus, okay, and then it will simply be equal to, so this part is actually, if you take the mod, it is nothing but V max 1. So, it will be simply lambda minus omega d by lambda plus omega d whole to the lambda by 2 omega d. Okay. So, if you do the, of course, there can be, we can also say that what will be lambda minus 1, the ratio inverse, that is which will be V max 1 by V max 2, that will be simply lambda plus omega d by lambda minus omega d whole to the lambda by 2 omega d. Okay. So, finally, you will have an interesting answer, okay, for our problem. Now, we will do something, we will try to find this result in different limits. Okay. So, if let us say, if we have very strong damping. So, in general when we say overdamped, that means lambda is greater than omega 0, but if we say strong damping, that is even stronger, that means lambda is very greater than omega, and that also means that omega d will then be equal to lambda square minus omega square whole to the half, and you can write this to be equal to lambda times 1 minus omega square by lambda square whole to the half, and just as we do in physics. So, we can approximately write this by expansion lambda times 1 minus omega square by 2 lambda square, and which will be equal to lambda minus omega square by 2 lambda. Okay. So, that is something we have to understand over here, and this is the case for strong damping. If we have this value of omega d, then what to do? Then of course, this chi inverse will simply be equal to, so I can write then lambda plus, so omega d is nothing but lambda minus omega square by 2 lambda, okay, by lambda minus omega d. So, from this condition you know lambda minus omega d will simply be omega square by 2 lambda, okay, whole to the lambda by 2 omega d. Okay. Now, again you see whenever I am writing this lambda by 2 omega d, so omega d is now this. So, one can actually say that whenever I am doing this type of expansion, okay, let me first do this. So, this is actually, so what will be then lambda by omega d? So, that will be simply pretty close to half, because when omega is very small, I can write lambda is almost equal to lambda omega d. So, I can actually write lambda by 2 omega d almost half. Okay. So, that I can use over here, and I can write this with the different color 1 over half. Okay. And of course, this is the approximation over here. So, that is why I just do not put this equal to sign over here, I just say this is like this, okay, this limiting value, and you will have, so 2 lambda minus omega square by 2 lambda by omega square by 2 lambda 1 half. Okay. I can say that this I can easily manage by doing some calculations. So, this is 4 lambda square minus omega square, which can be 4 lambda square, and here it will be omega square. So, this will be reasonably equal to 4 lambda square by omega square whole to the half, and your final ratio will be 2 lambda by omega. Okay. So, that is the ratio. What happens near critical damping? So, I just write this question, what happens to chi inverse near critical damping? Of course, just one question, that we start by saying that we have to evaluate chi. You can do chi as well. So, chi will simply be then omega by 2 lambda. Okay. It is just whatever you want, there is no problem. So, what happens to chi inverse near critical damping, or chi, okay, or chi. I just try with chi inverse, and chi will be simply 1 by that. Okay. So, near critical damping, so it is not exactly at critical damping, because critical damping permits another type of solution, right, that you know, it is not exactly the overdamped solution. So, near critical damping, but not exactly at critical damping. Okay. Near critical damping, what happens? Lambda is very close to omega, and then now lambda and omega, they are very close, omega d tends to 0, and then this chi inverse will be equal to simply. So, chi inverse I just take again. So, lambda plus omega d by lambda minus omega d whole to the lambda by 2 omega d. So, you see that here omega d and lambda, they are not very close. Okay. So, you cannot write that as approximately equal to half. What you can write here is that, so you can write, so this will be actually, so near critical damping, you can write this is nothing but omega d tends to 0, okay, and then you can write this as omega d over lambda by 1 minus omega d over lambda. You can just write from this is equal to this, and then you also write half omega d over lambda. Okay. So, this is something very interesting, and then you can actually write. So, if omega d tends to 0, then omega d by lambda also tends to 0, then you can actually write this is limit epsilon tends to 0, you call omega d by lambda as epsilon, which is very small, as 1 plus epsilon by 1 minus epsilon 1 by 2 epsilon. Now, since epsilon is 0, then you can actually say this is reasonably 1 minus, so it is 1 plus 2 epsilon almost whole to the power 1 by 2 epsilon. Okay. I can also write this as 2 epsilon is also tending to 0. Do you know this limit? This limit has a very interesting value, this is equal to e, that is the exponential e. Okay. And then, so chi will actually be e to the minus 1. Okay. So, you see that near critical damping, this ratio has a very fixed value, which is 2 point whatever 718. Okay. And then here you will have something 2 lambda by omega. So, in the limit of strong damping, this ratio still depends on the damping coefficient, and so whenever I write omega, I am sorry, I have to write everywhere omega 0, not omega. I am sorry for that. So, you just change everywhere omega as omega 0. Yeah. Okay. So, it depends still on the medium, okay, and the nature of the oscillator, because the natural frequency is there. But when this is nearly critical damping, okay, then somehow you see that there is no meaning of which oscillator you are choosing and which medium you are choosing for the ratio. The ratio is a natural constant, okay, and that is the beauty of this problem. Thank you very much.